In this video, we'll discuss ensemble properties, or how, given all of the structures of a particular molecule, how do we figure out various properties of interest. Okay, so we've spent the previous few videos talking about energy minimization, geometry optimization algorithms. So those are ways you can get the lowest energy structure of a given molecule or collection of molecules. So the issue is that for a lot of properties, the lowest energy structure, while it's some of the most important structures, is not the entire story. In fact, there are contributions to those properties from other structures slightly higher in energy, usually a lot of them, that contribute less, but there are usually, as I said, a lot of them. So what we need to do is we need to average over the contributions of all structures, not just over the properties at these low energy structures. Okay, so how are we going to do this? So let's say we have some general property of a molecule called A. Now what could A be? A could be something like the energy, energy, pressure, some kind of bond length, some type of distance between things, some type of, who knows, velocity. There's lots of any kind of property that this could particularly be, which depends on the position in space. So if we're at a particular position in space and we know this, we know what the value of this property is. Okay, so we'll say that the average value, or the expectation value of this, sometimes you'll note that in kind of this bracket notation, kind of the more quantum mechanics type notation. Sometimes the more thermodynamics or statistical mechanics way to denote that might be an A bar, the bar just being for average values. So we said we need to average over the contribution of all states. So what we're going to do is we're going to sum from I equals 1 over all states to where I equals, if we have m states from I equals 1 to m, the probability of being in that state times the value of that property at that state. Okay, so this would be if we had what is called a discrete system. So if we have a specific number of different structures, we could sum over all of them. So as I said, the two components that we have there, it's going to be the probability that we are in state I, probability of state I, and then the second part is the value of A in state I. Now this formula might look somewhat familiar. This is just the formula for a weighted average. So this has, so we have the weighted average probability that we're in that state times the property value in that state. Okay, so what do we get these probabilities from? So there's a lot of nuance here about statistical mechanics stuff. There's a lot of nuance about what kind of ensemble we're in, what kind of thermodynamic variables we have. If you're a person who's a stat mech expert or you're studying to be one, you might not like this and this might not be the right choice for you, but we're going to proceed here under a certain kind of assumption, and we're going to say that we have the probability of our state is proportional to the Boltzmann factor of that state. So the probability that we're in that state is proportional to e to the minus the energy of that state divided by the Boltzmann factor times temperature, where temperature is some specified value, which is the same for all states. Okay, so as I said from the StatMech videos before, that's called a Boltzmann factor. This works for certain kinds of ensembles, but not others, but I'm just going to go with this for now because this is one of the simplest cases. Okay, so we got our Boltzmann factor that we're going in there. So now we need to normalize this because the Boltzmann factors are not all going to sum up to 1. If we sum up all these probabilities over all of our states, that equals 1, but these do not necessarily do so. So from the StatMech videos earlier in the thermodynamics playlist, you might notice a thing called a partition function, Q, which would be a sum over all states of the Boltzmann factor of those states. So partition function equals sum of all Boltzmann factors. Then if you have a continuous system, then you would integrate over all of the coordinates of that system. So if there are n coordinates there, or 3n coordinates, or whatever we have, we'd have e to the minus energy at all of those coordinates divided by kt. Okay, so if we have a discrete system, it is a sum. If we have a continuous system, then it works as an integral. So classical mechanics will have a lot more cases where we have continuous. Quantum mechanics, there'll be more cases where you have discrete. Take it as a case-by-case basis. All right, so then what does our probability become? So the absolute probability is equal to 1 over the normalization constant Q, sum over all the Boltzmann factors, times the Boltzmann factor of that particular state. Okay, so that's the probability that we're in our given state. Then we need to multiply that times the probability that we're in that state, and then for continuous states, integrate over all states. So what this becomes, once it's all said and done here, if we have a bar equals integral over all our n dimensions, we have the probability is 1 over q e to the minus energy of r to the n over kt times the value of a at that particular location in space, or in phase space, as we say for all those coordinates. So this q, as I said, was an integral as well, so that's in the denominator there. So what we end up is that our average property is a ratio of two integrals. So we have integral of, let's put the value of our property at that particular state over times the Boltzmann factor at that state, divided by the integral over all the states of the Boltzmann factor of all of the states. Okay, so this is like a weighted average. So we have a weighted average, or in this case, if the average is weighted by the Boltzmann factors, so we could call this a Boltzmann weighted average. Okay, now the issue is, as I said, for a general molecule, we have n atoms and 3n coordinates, or, well, I've been using n here, so let's just say we have n coordinates. So this is an n-dimensional integral. So if we have 100,000 atoms, n is 300,000. So obviously we can't do an integral over 300,000 dimensions. That would be an obtusely difficult integral to solve. So what are the possibilities that we can use to solve these integrals and have any hope of getting any kind of property we want? What's the average energy of a system? What's the, average moment of inertia of a protein? What's the average distance between two given atoms? All those kinds of things that we want to know about molecular systems. How do we have any hope of solving these integrals here? Okay, so as I said, for very simple functions, you can just do the analytical integral. So for very simple functions, you can just go ahead and solve this integral. That is highly unlikely for a general molecular system, not only because our potential energy is complicated, but we have many, many dimensions which have dependence on each other. So that's very unlikely that analytical integration is going to work. So that seems to be out in general. So basically, we have to find some way to numerically integrate it, some way to approximately solve these integrals. So the rest of this chapter is sort of dedicated to various ways of approximately solving these integrals for various properties. So the things we could do things like solving that on a grid. So we could say, well, if, for example, if dimension 1 goes from 0 to 100, I I could pick 100 different values, 1, 2, 3, 4, 5, 6, and then try to do the integral that way, kind of like a Riemann sum type integral. The problem is that is also unlikely because, as I said, there are many, many dimensions. So if we have to do, let's say, 100 points in each dimension, if there's 1,000 atoms, that's 3,000 atoms. So that's 10 to the 3,000. So we're not going to be doing 10 to the 3,000 different evaluations of all these things. So that's very unlikely at all. So except for very simple cases, we're also unlikely to directly evaluate it on a grid. That's a rather brute force solution, as we would say. Another option is to do a time average. So this is what we do in what's called molecular dynamics. So there's some theorems that basically say that averaging over space is equivalent to averaging over time. If a system obeys what's called the Ergodic Hypothesis, what we'll get is that an integral over all of the spatial dimensions is equal to an integral over an infinite amount of time of that property at a value of time. So basically, over a long period of time, the system will explore all relevant states with the proportion which is consistent with their probability as computed by their Boltzmann factors. So basically, we can simulate the system through Newtonian dynamics, classical mechanics, whatever you prefer, over a large amount of time. And by simulating the system for a large amount of time, what we'll end up with is averaging over that time effectively what would be something very similar as if we were to just compute directly the integral of these properties over various parts in space. That the places that the system goes over time are in proportion to their various probabilities in the whole space of all these coordinates. Okay, and the last possibility we could have is we could do some type of random averaging. So we could use the properties of random numbers to choose various, hopefully cleverly choose various random locations on this potential energy surface in order to get a good approximation for what this property is. So this is things like Monte Carlo, yes, named after the location in France with lots of casinos, Monte Carlo, and we'll also look at the naive Monte Carlo and also a specific algorithm called Metropolis Monte Carlo, where you have some method for selecting structures randomly, and hopefully as you select them randomly, you are going to integrate over hopefully all of the relevant configurations in a correct proportion if you choose these random numbers to be selected carefully. So that is the rest of this chapter, is finding various ways and looking at a few nuances of calculating these ensemble properties for collections of atoms that we move over time.